So where we left off, we were drawing in a vector, and depending on whether it said bearing or not, we chose a north, south, east, west map, or if it did not talk about bearing or navigational directions, then we went with an XY axis. So it depends on the actual problem that you have, how you go about drawing the vector. The bearing ones, if it's a quadrant bearing, it's going to be written in the form, in the case of problem C here, starting in the south 60 degrees to the west. And so we know we're going to start on the south. If it is a true bearing, then you always start at the north and go clockwise. The other thing we're going to look at here is sets of vectors, and we can have parallel vectors, equivalent vectors, and opposite vectors. So the first one we want to look at are parallel vectors, and for parallel vectors, they have the same or opposite direction, but not necessarily the same magnitude. In other words, the vectors themselves do not have to be the same length, but it's just like parallel lines. They need to be equal distance apart. They need to be going in the same or opposite direction. So I'm going to scroll down here a little bit, and we'll look and see what some of our parallel vectors would be. So again, they can be going in the same direction or opposite direction, but not necessarily the same if I can get out of that screen, the same size. So we're looking at maybe this one, we've got B, C is going the same direction, E looks like it's parallel, and F. So really everything but D, those would all be parallel to each other. The next type of vectors we're looking at are equivalent vectors, and they have the same magnitude and the same direction. So they're obviously identical. And we want to identify some of those. My identical ones, it looks like A and C, because they look about the same length and they're definitely going the same direction. So those would be equivalent vectors. Opposite vectors have the same magnitude, but are going in the opposite direction. So we want something the same length, but going in different directions. So an example of that looks like A and E. So exact opposite directions, which means they still need to be parallel to each other. The other thing we need to notice about this is the vector opposite A is written as negative A. So E can also be called negative A because it's going the opposite of it. I would assume then that in turn A would be negative E. When two or more vectors are added, their sum is a single vector called the resultant. And so this is where we're going to add vectors together. We've got a couple of options for doing that. One way is called the triangle method, and what we're going to do is we're going to make a triangle. And you do this by taking your vector A and you're going to attach B to that by translating it, and that means it needs to remain in the same direction and it needs to remain the same length. So what you could do for this, and I'm going to draw a little line over it, is I'm going to take my my vector here, and I'm going to literally translate it. So it's going to stay the same direction. So I'm going to pick it up and over so that it's parallel to my original. So now you can see that that's what I've done. I've just moved it over so it's remained that same direction. And now it looks like the picture in step 1. And then you're going to draw a line from the beginning of A to the end of B. And obviously I'm just kind of adding on here, and they've done that in step 2. We'll get a green color here. And I'll go from the end of the tail of A to the head of B there. And so that new green vector that we made, that's called the resultant. So that's combining them all together. That's our direct shot from point A to point B. So imagine if we're going from, we start here at the tail of A, and we go a certain distance, and then we turn left and we go along B. If we could have made a straight shot instead of taking that turn along the road, we would have gone down A plus B. Then you have the parallelogram method, and that's where you're going to make a parallelogram. Kind of depends on the situation that you have. To find the resultant of A and B, follow these steps. It says step 1, translate B so that the tail of B touches the tail of A. So I'm going to again make a little vector here over B, so that I can move that. And we're going to translate this one, so that means it has to stay the same direction, and we're going to touch the tail ends there. So now we've got a picture that's like this happens in step 1, right here. So what you really have is you have 2 sides of a parallelogram. So the idea would be to finish our parallelogram. So we need a segment that's parallel to A on the other end. Let me do a line. So to keep it kind of going all the same direction, I'll just move it like I did the last one. Oop. It is not going to let me do it. There we go. So move it over here so it doesn't rotate any. Then I'm going to do another one for B. And bring it down here. So I've completed my parallelogram. And then I'm going to go from the center, or where my endpoints touched, from A and B, and I'm going to go across the diagonal. And that's going to be my new ray, or my new vector A plus B. So those are the 2 ways. We had the triangle method and we had the parallelogram method, both of which make triangles and parallelograms. So I'm going to try it out. We have a problem here. It says orienteering. In an orienteering competition, Tia walks north 50 degrees east for 120 feet and then walks 80 feet due east. How far and at what quadrant bearing is Tia from her starting position? So I'm going to, I've got north, south, east, west, so I'm going to do a coordinate here. And I have north, I have south, I have east, and west. And it says that Tia, so this is a quadrant bearing because of the way it's notated here. And I want to go 120 feet, and then she walks 80 feet due east. So I want to get out my protractor so that I can measure 50 degrees east of north. So I'm going to turn it around here, line it up with my origin. And so that I've got the left side along the north axis, and I want to measure over 50 degrees. So I'm going to put a little mark there. That's pretty close. Move my protractor. I'll make a little potential vector here from the origin through that dot. And then I need something to measure its length. I've got 120 feet, and I'm also then going to move 80 feet. So what I'd really like to do is give it increment so that it's a factor of both 120 and 80. So I'm actually going to make 1 centimeter equal to 40 Let me try this a little bit different way here. So I'm going to make 1 centimeter equal to 40 feet. So when I measure off with my ruler, I want to measure off 3 centimeters because that's going to be equivalent to 120 feet. And then also I'm going to put a little dot there because that's where I want to mark my vector off. I want to stop there. Okay, so there's my vector, and if I've done the right thing, I should have $50 degrees here. Then it says that they walked 80 feet due east. So straight from that point that I stopped at, I'm going to do another vector from the end of where Tia was walking and parallel with east. Okay. And I know that that's 80 feet due east, so I wanted that to be a multiple of 40. So that guy needs to be marked off at 2 centimeters. And I'm going to shrink my little vector here. That's pretty good. You can actually see that I have part of a parallelogram. So I'm going to finish off my, actually I've got 2 sides of a triangle is what I really have, because I've got the tail of one and the head of another. When we're doing a parallelogram, we put the 2 initial points together. So I want to complete this triangle. and it says how far and at what quadrant bearing is Tia from her starting position. So I want to measure then the angle that's formed with the black vector there. So I'm going to get my protractor out and I'm going to measure that angle because that'll tell me her quadrant bearing. And then I also want to measure the length then of the black vector. So it looks like that Tia is, it looks to be about 60, about 63 degrees. So I'm going to add to that her bearing is north 63 degrees east. And then how far is she? I need to measure my vector. And I look to be about 6 centimeters. So I want to translate that over into what we determined to be the scale. So again, she was north 63 degrees east. That's her current quadrant bearing. And then it looks like that's 6 centimeters. But I already said that 1 centimeter is equivalent to 40 feet. So we want to determine then how much that's going to be. So it looks like the x, that would be 6 times 40, which is 240 feet. So she's 240 feet from her initial position, and her quadrant bearing is north 63 degrees east. For the next little guy, we're going to take these vectors and I'm going to translate them, and I'm actually going to do a parallelogram this time. So I'm going to move V there, and I'm going to move W just so we can see it a little bit better. Get some space to move. And when you do a parallelogram, you want to connect the initial points. So I am going to then complete my parallelogram. So I want to make a side that's parallel to V here. Let's see if I can get it to move. There we go. And then one that's parallel to W. Okay, so there's our completed parallelogram. Then we want to go from the initial pieces that we drew, and I'm going to make a new vector. So we go from those endpoints and we're going to go across, and this is our new vector, and we would call that v plus w. When you add two opposite vectors, the result is the zero or null vector. So opposite vectors, again, they're going to be parallel, they're going to be equal length, equal magnitude, but they're going to go in completely different directions. So if we were to add those two together, they would just negate each other and they would both be zero. Multiplying vectors by a scalar. So a scalar we talked about as being a multiplier. It has nothing to do with a direction. Says if a vector v is multiplied by a real number, a scalar, then we actually give absolute value. K times absolute value of v. Its direction is determined, however, by the original sign of k. So we've got if k equals 0, so if we've got a negative out in front, or I'm sorry, if k is greater than 0 and we have a negative out in front, then the vectors are going in the same direction. If it says less than 0, then it's going to go in the opposite direction that it's originally stated as. All right, so we're going to do, it says operations with vectors. We have multipliers, and it's exactly what it says it is. We're going to take x and we're going to make it 3 times what it is right now. So we want to triple the length of x. So think about that as being 1, 2, and then I'm going to add another one to it here. So that length is 3x. So I'll make a big one to kind of go with it. And what you would probably do is measure x, and then you just take that measurement and multiply by 3. So this one is actually 3x now. And then for y, that gets a little bit sneaky because we only want it 3/4 the length of y. So again, I would measure the y vector, and then we're going to have to multiply this by 3/4. So we only want 3/4 of that length. All right, so here's my y vector. And, you know, that's about half, so we want a little half more. That's going to be about 3/4 the length right there. The correct thing would be to do instead of approximate that would be to measure your, I think I'm going to have to go get the ruler. You need to measure your y. You could do it in centimeters. So the original amount was, looks like to be about 4.5. So you want to take that 4.5 and multiply by 3/4. Which I would say I'm pretty much right on there. So it's 3/4 the length of the original one. Now, you'll notice too that this says negative though, negative 3/4. So what does that mean? It means that your vector is now going in the opposite direction. So I want to turn the whole thing around and go the other way with it. Hopefully I'm still the same length. I'm going to take it up there and compare it. It's about the same now. You do want it parallel. So I'm going to bring it over here. I'm going to match it up with the endpoint because now it's going the opposite direction that the original vector was going. And then I'm going to connect. I'm going to make that triangle vector. Now the green one represents 3x minus 3/4 y. Okay, for the second one here, it says draw a vector diagram of each expression. We have a minus c plus 2b. So the a is going to stay the same because it's positive. Negative c means that the c vector is going to go in the opposite direction. And plus 2b means for b, the direction is going to stay the same, but we're going to double the length. And then we're going to basically play a little connect the dots here. So we know that a is going to stay the same. I'm going to duplicate a for us. Give us a little more space to work with. And then minus c means that c is going to go in the opposite direction. So the length is the same. We're just making it in the opposite direction. So I'm going to connect those parts. And then plus 2b, b is going to double in length. But it's going to remain the same direction. So there's one. And then so I'm going to do a big one. We've doubled it. Okay, so that would represent 2b. And we'd attach it on the end of c. So this is kind of going a little bit out of our way. We've gone a, we've gone minus c, we've gone plus 2b. If we had gone directly from start to finish, what would that look like? And so from start to finish, I would take the initial side of a to the end of 2b. And that black vector there then would be a minus c plus 2b. So I'm going to have you actually stop there, and I've changed the assignment a little bit, so we'll do the application problems when I get back. And that's, I'm going to have you do page 488, numbers 2 through 34 evens instead of what's at the end of these notes. Have a great weekend, and I'll see you on Tuesday. Bye.